Welcome to this explainer. Look, if you work anywhere near industrial pipelines, oil and gas, power generation, or modern chemical plants, you already know the deal. Keeping high-pressure fluids and gases safely contained, that's literally the most important job on the site. So today, we're diving right into the exact standard that makes that containment possible. We are talking about ASME B16.5.
But first, picture this. You're in the final stage of commissioning a high-pressure steam line. Everything looks absolutely flawless. The bolts are torqued exactly to spec, the gasket is brand spanking new, and then you hear it. Just a slight hiss. So why does that happen? Well, in 90% of cases, the true culprit is actually an overlooked face mismatch, or maybe a surface finish that just doesn't align with the gasket.
And we all know a hiss isn't just some minor annoyance you can brush off. It's an early warning sign of a catastrophic shutdown, or honestly, an explosion. A flange isn't just a basic bracket to bolt two pipes together. It's a highly complex sealing system. The geometry has to be meticulously matched to the operating pressure, the temperature, and the specific fluid media running through it. This is exactly why the industry relies on a super strict set of building blocks to guarantee safety.
To break this all down, here's our game plan for today. We'll quickly cover the foundation of flanges, look at pressure and temperature ratings, and check out the anatomy of flange types. Then we'll get into flange faces and sealing, compare ASME B16.5 with B16.47, and finally, check out the big 2025 edition updates.
All right, starting with Section 1, the foundation of flanges. Let's look at the actual DNA of the industrial piping world.
So, what exactly is ASME B16.5? Put simply, it's the authoritative standard for steel pipe flanges and flanged fittings. Think of it as the universal blueprint. It standardizes everything: the dimensions, the pressure and temperature ratings, the materials, even the testing requirements. Specifically, it governs nominal pipe sizes, or NPS, from tiny half-inch pipes all the way up to massive 24-inch ones. It categorizes flanges into 7 primary pressure classes: 150, 300, 400, 600, 900, 1500, and 2500. So whether you're working with carbon steel, stainless steel, or nickel alloys, this standard is what ensures a flange manufactured in one part of the world will perfectly and safely connect to a pipe in another.
Moving on to Section 2, pressure and temperature ratings. Now that we know what the standard covers, how do these extreme operational environments actually interact inside the system?
We'll take a look at the inverse relationship between heat and pressure capacity here. It's pretty wild. As temperatures rise, the allowable non-shock pressure actually drops. Check out that Class 150 column. At a baseline temperature of anywhere from -20 to 100 degrees Fahrenheit, a Class 150 flange easily handles 285 psig. But if you follow that column down to 500 degrees Fahrenheit, that exact same flange loses a ton of its capacity, dropping down to just 170 psig. This is a perfect example of why you can't just select a flange based on pressure alone. The thermal environment is a massive, absolutely critical variable.
All right, Section 3, the anatomy of flange types. So how do we physically shape these connections to handle such intense parameters?
You can see the core flange types here, and each one is engineered for a very specific job. Up top, we have the weld neck flange. This one is circumferentially welded directly to the pipe neck, which cuts down on turbulence and erosion. That makes it the absolute go-to for critical high-stress applications. Below that, the slip-on flange literally slips right over the pipe and is fillet welded. It's way easier to align in fabricated applications. Then you've got the blind flange, which you use to completely blank off a pipeline or a valve. We also have the socket weld for your smaller pipes, the threaded flange for low-pressure stuff where welding just isn't needed, and the lap joint. That one uses a loose flange behind a welded stub end, which is an absolute lifesaver for systems that need frequent dismantling. Which brings us to Section 4, flange faces and sealing. Having the right flange type is great and all, but the actual seal happens where the flange face meets the gasket. Let's zoom in on that micro level.
You basically have 3 primary flange faces to choose from: flat face, raised face, and ring-type joint. But honestly, the face geometry is only half the story. The surface integrity is governed by what's called ARH, or arithmetic average roughness height. For instance, a raised face usually needs a serrated spiral finish with an ARH between 125 and 250 microinches. On the flip side, a ring-type joint uses a metallic ring compressed into a groove, so it needs a super smooth finish of less than 63 microinches. The big takeaway here: matching the face type with these exact surface roughness limits is what actually creates the friction you need for a leak-proof seal, without accidentally creating deep radial pathways for pressure blowouts.
Jumping into Section 5, ASME B16.5 versus B16.47. So what happens when a procurement officer or an engineer needs to build something way bigger than a 24-inch diameter?
Well, this is exactly where ASME B16.47 steps up to the plate. Like we talked about, B16.5 maxes out at a nominal pipe size of 24. For the really massive industrial pipes, ranging from NPS 26 all the way up to 60, B1647 takes over. But here's the catch. B1647 actually splits into two different series. You've got Series A flanges, which evolved from the older MSS SP44 standard. These are thicker, heavier, and stronger, built to handle more external loads. Then you have Series B flanges, coming from the old API 605 standard. These require more fasteners, but they're smaller overall, which means a smaller bolt circle diameter and less flange movement after installation. When you're dealing with pipelines on this kind of massive scale, knowing which series to use is a big deal.
Finally, Section 6, the 2025 edition updates. Because these standards aren't just frozen in time, they are constantly evolving. The newly released 2025 edition, which becomes totally mandatory by January 1, 2026, brings some seriously targeted upgrades. It tackles real, on-the-ground industry pain points. For example, it fixes some critical material grouping errors, like the classification of N08800 alloys, and adds crucial data for nickel, duplex steels, and titanium to handle insane temperatures, from -29 all the way up to 815 degrees Celsius. It also brings in strict low-stress sealing clauses to play nicer with modern low-preload gaskets. On the quality control side, high-stress areas on Class 900 to 2500 flanges now require 100% ultrasonic or magnetic particle testing, plus mandatory full-process traceability. But maybe most importantly, it adds dedicated ratings for green hydrogen and carbon capture systems, bringing the standard right in line with the global push for low-carbon energy.
Which really brings us to a final thought here. We've just seen how ASME B16.5 meticulously governs every single millimeter and every degree of pressure for traditional oil, chemical, and steam pipelines. But as we completely overhaul our infrastructure for a low-carbon future, a future where we're handling incredibly volatile stuff like liquid hydrogen and captured carbon, how are these universal blueprints going to continue evolving to keep the world's most extreme new energy projects safe? It is an absolutely fascinating engineering challenge. Thanks so much for joining me on this explainer, and keep exploring the mechanics that hold our industrial world together.